Let's review the method of cylindrical shells for calculating volume and work on an example. So the first thing we need is we need our function to be both continuous and non-negative. And we're going to define R to be the region bounded above by the graph of f of x and below by the x-axis. Bounded on the left by the line x equal to a, and on the right by the line x equal to b. Let me draw a picture for you. So here's our y-axis, and here's our x-axis down here. And we're going to have x equal to a as the left boundary, and x equal to b as the right boundary, and we have some function y is equal to f of x. So let me label the left boundary, let me label the right boundary. Just as a reminder, it's bounded from below by the x-axis, so the x-axis here forms a lower boundary, and we are going to rotate about the y-axis. So I'm going to put a little loop right here. We're going to call this region R, and why don't we shade that in? So let's color that in like this. Okay. So as we discussed in the last video, what we're going to do is we're going to chop up parallel to the axis of rotation like that. So you can see that your little bit of thickness lies on the x-axis. Okay. So when we go to write down our formula is going to be the volume is equal to the integral from a to b. You're going to have 2 pi times x times f of x dx. And this number, x, is the radius. And this f of x is the height of my cylindrical shell. And this entire first expression here, this is the circumference of a circle. So if you can remember how to get the area of the surface area of a cylinder, which is this whole expression here, then you can just multiply by the little bit of thickness to get the volume of the shell. So as a quick review, the key idea was that we chopped up parallel to the axis of rotation. We have to determine if it's a dx or a dy situation, and then we want to calculate the limits of integration. You can find this by looking at your picture and write down what is the radius and what is the height. So let's do example 1 together. You can see this in action. So I'm going to draw a set of axes here. So here's the y-axis. Here's the x-axis, like so. Okay. And let me label, here's 0, here's 1, here's 2, here's 3, here's 1, like that. My function is 1 over x, so maybe it kind of comes down like this. Maybe it comes up like this. Something like that. Okay. And our function is the graph of f of x equal to 1 over x, and the x-axis is going to be the bottom boundary over here, and we're going over the interval from 1 to 3. So this is x equal to 1, this is x equal to 3, and I want to shade in this region that I'm rotating. So I'm rotating this region in between my curve and the x-axis, and x equal to 1 and x equal to 3. So this region right here is the region R that we're working with. Okay, so I think the final thing I need to do is I need to label my axis of rotation. So my axis of rotation is going to be the y-axis. So let me put a little loop about the y-axis like this. And we know we need to chop up parallel to the axis of rotation. So I'm going to chop it up like this. Okay. So I've drawn my picture. Um, I can see that my little bit of thickness right here, this little bit of thickness, that's a dx type situation. So I think I'm ready to set up my integral. My integral is going to be a dx integral because that little bit of thickness lies on the x-axis right here. And the smallest my x can be is 1, and the largest my x can be is 3. And then my circumference of my shell is going to be 2 pi r, and the height of my shell is going to be f of x. So let me write in what those pieces are. That's going to give me a 2 pi. The radius is really going to be given by the x values. So x is starting at 1, so the smallest radius is 1. I'm going to iterate through each of these shells. The biggest shell is going to have a radius of 3 over here. And all the radii in between are determined by whatever x value we have from 1 to 3. So my radius is going to be x. The height of my function is going to be the function value evaluated at x. So that's going to be 1 over x. And then I have dx like this. Okay. So looks like we got some nice cancellation here. X times 1 over x is just 1. So really my integral becomes the integral from 1 to 3 of 2 pi dx. And, I can factor out the 2 pi, so that's going to become the integral from 1 to 3 of 1 dx. That's just going to be equal to 2 pi times x as we go from 1 to 3. And 3 minus 1 is 2. 2 times 2 pi is 4 pi. So we'll have 4 pi units cubed because it's going to be a volume. So let me just highlight this as our final answer. Maybe I'll include an extra picture. So if we imagine that we're working with this particular shell right here, I don't know if you can see that, I was just shading in this shell right there. Then when I reproduce this, picture looks like this. Here's my shell, it kind of comes all the way around. Try to draw it symmetric on both sides of the y-axis, kind of comes like this. Okay, and it has a little bit of thickness. So let's indicate a little bit of thickness like that. So that's the shell that we were drawing, and the radius of that shell is given by x, and the height of this shell is given by 1 over x. All right, everyone. We'll look at more examples together in class. Take care.